All right, welcome to Next Gen Manufacturing. Today we're going to dive deep into the incredible materials that are literally building our future, making everything lighter, stronger, and way more efficient. But before we can actually build with them, we've got to answer one absolutely crucial question. How can we trust them?
You see these incredible composites everywhere now, right? From the wings of a jet to the body of a supercar, they promise this revolutionary performance. But in these kinds of jobs, where failure is just not an option, how do we prove, beyond a shadow of a doubt, that they're safe? Well, that's the hidden science we're getting into today.
So, to build that trust, we have to start small. Really small. We've got to go microscopic to hunt for these invisible flaws that could bring down an entire structure before it's even off the drawing board. And our number one enemy has a name: porosity. So what is it? Well, think of them as these tiny, microscopic air bubbles that get trapped inside the material when it's being made. Each one of those little voids is a potential weak spot, a place where a crack could start. It's like a hidden danger lurking inside. And believe me, these aren't just minor little imperfections. Get this, a porosity level of just 5%. That means just 5% of the material is empty space can slash its strength by as much as half, 50%. So yeah, the mission becomes crystal clear. We have to find these voids. So how do you find an enemy you can't even see? Well, there are basically two strategies. On the one hand, you've got destructive methods. It's kind of like the ultimate autopsy, right? You can burn away or dissolve the plastic part to get a super precise measurement, but you destroy the part in the process. Then, on the other hand, you have the really cool stuff, non-destructive imaging, like ultrasound or X-ray scans that lets us peek inside and map out the flaws without leaving so much as a scratch.
Okay, so finding voids is super important. But a great composite isn't just about what's not there, it's about what is there. Real strength comes from the connections, and specifically, the bond between a single reinforcing fiber and the resin matrix that holds it all together. This is our next building block of trust.
You know, the best way to picture this is to imagine a microscopic handshake. This interface, as it's called, is where the fiber and the resin meet and grip onto each other. If that handshake is weak, the material just falls apart under stress. So scientists have come up with some incredibly clever ways to measure just how strong that grip really is. The first method is just beautifully simple. It's called the pull-out test. You basically take one single fiber, stick it in a tiny drop of resin, and wait for it to harden. Then you just pull it out. A machine measures the exact amount of force it takes to break that bond. It's a really direct, elegant way to measure the strength of that handshake. The fragmentation test is a little different. Here, you put a fiber inside a bigger block of resin, and then you stretch the whole thing. The resin stretches, but the fiber, which is stronger and more brittle, starts to snap into smaller and smaller pieces. Eventually, the pieces get so short that the resin around them can't transfer enough force to break them anymore. And the final length of those little fragments tells you exactly how well that handshake was transferring the load. It's pretty smart. Now this one is really cool because it lets us measure the bond inside an actual finished composite part. You take a real sample, you polish it up, and then you use this tiny diamond-tip needle to literally push on the end of a single fiber until its bond breaks. This gives you what's called an in-situ measurement, the true strength of that bond out in the wild, not just in a lab. Okay, so we've found the voids, we've tested the handshake of a single fiber. Now it's time for the main event. We're going to take a full sample of the material and put it through an absolute gauntlet of forces to find its ultimate breaking point.
First up is traction, also known as a tensile test. Honestly, it's the most fundamental test of strength. You just clamp a sample in a machine and pull it apart until it snaps. Simple as that. This tells you its ultimate strength and how stiff it is. Next, we've got flexion or a bend test. This is exactly what it sounds like. It simulates the forces you might see on an airplane wing or a car's suspension. Bending the sample till it breaks shows you how it handles that complex mix of being pulled on one side and squashed on the other.
And then, of course, we have compression, which is the total opposite of traction. Instead of pulling, we're squeezing. We crush the sample to see how much force it can take. This is absolutely critical for things that have to bear a ton of weight like landing gear.
And finally, we have shear. Now, this is a really big deal for composites, and often a tricky weak point. Shear forces try to make the layers of the material slide past one another. And since composites are built up layer by layer, this can be a huge vulnerability, leading to a type of failure called delamination.
Now, what's fascinating here is just how many different ways scientists have figured out to test for this one specific weakness. Look, you don't need to memorize the name Io-Supascu shear test. The big takeaway here is that this shear variety, from bending little beams to twisting tubes, shows you just how seriously engineers take the threat of shear. They are not messing around.
So here's the crucial point in all this. Passing a test with a small, perfect little sample in a lab is one thing. The real challenge, the real magic, is scaling all this science up to guarantee the safety of huge, complex structures out in the real world.
And this is where all that tiny, fundamental science pays off in a huge way. Those same principles are used to qualify everything you're seeing here. The high-pressure tanks that hold natural gas in vehicles, or breathable air for firefighters, critical car parts like drive shafts, and of course, massive aerospace structures where safety is everything.
When you boil it all down, this whole process, from the micro to the macro, is really the science of trust. Next-gen manufacturing isn't just about cooking up new materials. It's about building this unshakable foundation of data that proves they're ready for whatever the world throws at them.
There's a quote that just sums this all up perfectly. The future belongs to structural composites, where reliability is the master word. It's so true. Without this painstaking, verified reliability, any innovation is just a cool science experiment. It's the rigorous testing that turns a novel idea into a technology you can bet your life on.
And all this leaves us with one final big question. When we can absolutely guarantee the performance of these advanced materials, right down to the microscopic level, what does that unlock? Lighter planes that use less fuel, safer cars, more resilient infrastructure? What kind of future can we build on a foundation of materials that we can truly, scientifically trust?